Q minus W equals to delta H plus K plus P. Previously, we just put in equals to out. But if you move them around, it's the same equation. So in this sense, actually, you can also remember this in an easier way. Like if you don't want to write in and out, right? Closed system is Q minus W equals to delta U. Open system is Q minus W equals to delta H. That's pretty much the only difference. Of course, don't forget the K and PE lah. It's just that closed system usually we don't have that, so we don't take that into consideration. Okay, so now so in this case, based on the TdS relation that we derived earlier for entropy, we put the change in the Q as TdS, right? And then TdS is equals to delta H minus V dP. So this was derived in earlier slides. You can check them back. So here we say that the change in the Q is actually dH minus V dP. So you sub this into this equation, then you will see that the delta H will cancel off, and you are left with the work is equal. So the work is actually equals to V dP plus d change in K and change in P, and that's the integral of it. Right. Okay, so actually this is nothing new that you have nothing that you haven't learned. It's nothing too new. So when we ignore kinetic energy and potential energy, then the work done in the steady flow work, or the work done in the steady flow process, is actually the integral of V dP. So for incompressible working fluid, whereby specific volume is a constant, then the reversible workflow is just negative V delta P. I'm just ignoring K and P here. So for the steady flow of a liquid through a device that involves no work interaction, then this work term is 0. This is actually the Bernoulli equation, but for us, for those of you who have learned the Bernoulli equation, then you will see that the pressure term here is actually the flow work in this case. Right, this one is just to show that the larger the specific volume, the greater the work produced by a steady flow device. So here you can see that this equation actually is quite similar to what you use in closed system. In closed system, we say that, let's say, same thing. So here, this is for incompressible case. This is the equation, right? But in the closed system, we say that if you have isobaric case, so in both cases, you can see that we set one thing into constant. We say that work boundary is equal to P V2 minus V1, right? This is what we say for closed system. And now in open system, then we say that the working fluid is V delta P if we have incompressible work. So these are the similar equations, but they carry a slightly different meaning. So for closed system, that is the boundary work, the work done to push the boundary. So it is actually the work done for you to change the volume. So the driving force here is actually the P. So the higher this value, okay, actually it doesn't matter, both also important. But the main thing here is that the driving force here is actually not the P. The driving force here is this V. So the change in the V will change the boundary system. Then if the constant pressure value is higher, then of course the boundary work will be higher. While for the open system case, so this is boundary work. So the work done to push the boundary. As for the open system, this is what we call the flow work. So the work done in order to push the working fluid, or in order to allow it to move. So here, then the change here will be pressure, because pressure is the one that causes it to move, the difference in the pressure. And you can see that the denominating factor here is actually specific volume. Why is that the case? Because if it is an incompressible working fluid, then the specific volume here, the larger it is, then the more work you need in order to move this thing. You can also see an example of this in the following slide. Not a very good representation, but it is part of it. Okay, so here, example. Compressing a substance in the liquid versus gas phases. So you will see in this case, we have two different things. Remember, I mentioned that pump and compressor are the same thing, just that they work with different substance. Pump works with liquid, while compressor works with gas or vapor. We don't create any, we generally don't want something that works in both phases because it's very hard to control. So it's either work with pure liquid or work with pure vapor. So here you can see clearly from just the diagram as well, the TS diagram here. So here you can see that in these both cases, we are just approximating this as an isentropic process as well. You can see the delta S doesn't change. The S doesn't change, right? For both cases. So this is the case where you have a pump, while this is a case where you have a compressor. And we know that based on all this while you study PV diagram, LV diagram, you know that the V here is much larger compared to the V over here. Right? The V for the compressed liquid is always very small. The specific volume for the vapor side is always very large. If you just look at the table, you can also see that. So just based on that, you will see that the work done by a compressor will always be much larger than the work done by the pump. Meaning the pump will require a very small amount of energy in order for you to increase the pressure of the liquid. While you can see that, so like in this case, just look at the distance of the line. Actually, both of them are doing the same amount of work. I mean, the same type of work. Meaning pump is still increasing from 100 kilopascal to 1 megapascal. Compressor also trying to change this from 100 kilopascal to 1 megapascal. But the distance that it needs to go through is not the same. Because compressor will require much larger work due to the increase in the specific volume. So for these two cases, the way that we analyze the work done will be slightly different as well. So you can see from the equation here, compressing a liquid, meaning the case in the pump, this one. The work done here, we can approximate this with V P delta P, because we have learned that when let's say water is at saturated liquid or compressed liquid, the specific volume is about constant. Roughly, not exact constant, but it is about that. So when we are dealing with pump, then we can approximate this to be V delta P. We use one V value, and then we look at the change in the pressure, you can get the work done. So this is based on the actual information that you can get from a table for water. I believe this specific volume 0.001043 is the specific volume for saturated liquid water. And then when we look at compressor now, so we look at compressor. So for compressor, you cannot use V delta P, because we know that when a water, let's say, is at the vapor state, when you change from 100 kilopascal to 1 megapascal, the change in the specific volume is actually very high. So in this case, you actually cannot use the change in, you cannot use a constant specific volume, so meaning you cannot use the above equation. So what we do here usually is we find the change in the enthalpy state. So in a similar way where when you did calculation for your lab, we say that all the work change, the heat change, we just assume them to be the change in the enthalpy, right? So here we do the same thing. So you can see that instead of using V delta P, we use H2 minus H1 as well. Now we use H2 minus H1. And so we get the H value from the table. You will see that this is a change in the energy, meaning this change in the energy is caused by the work in. So this work in, you can see this value compared to this value. It is very different, even though both of them are trying to do the same thing, meaning increasing the pressure from 100 kilopascal to 1 megapascal. But yeah, the value here is actually very large. So This also shows that the larger the specific volume, the greater the work produced. And also for then again for compressing gas, you can't assume constant specific volume lah. So that's why it's not as you can't see it as clearly, but just by calculating for this, you can see that the difference is 500 times. Yeah. So about that. So this one I just mentioned it. So do not confuse between VdV and PdV because they represent the same different thing. Okay. So PdV represent the boundary work while VdP represent the flow work. Okay. So now that we have established this work, now let's take a look at some things like not to say something different, but we try to relate what we learned previously here. So now first thing we look at turbine. Okay. We look at a new term called isentropic efficiency. Isentropic process. So what was isentropic process again? A process where entropy doesn't change. Or in other words, we also can say that it's an adiabatic process lah. But usually we say isentropic process because we want to keep it to the entropy term. So isentropic process is a process where entropy doesn't change. So can you have a guess what is isentropic efficiency? Okay, so now let's look at this derivation first. Now, so let's establish something first. You see, we call isentropic process a process that doesn't involve heat transfer, right? Adiabatic process, so you don't have any heat loss, heat gain. So obviously, things like, let's say, an evaporator, boiler, condenser, this kind of thing cannot be isentropic process. There cannot be isentropic process for those heat addition or heat rejection process, because this process primarily involve heat transfer. So we are talking about process that usually are not supposed to involve heat transfer, like turbine in this case. Of course, sometimes we will have heat transfer due to accidentally heat gain from the surrounding or heat loss to the surrounding, depending on what's the temperature. Okay, so let's say we look at the turbine. We know what a turbine is. Turbine is used to extract work. So it's work out for turbine. That is the main thing. So this is the main focus for a turbine. Right, we did this in your test as well. This is the main focus. Work out. Sometimes we might have Q out or Q in depending on either the fluid temperature or surrounding temperature. What's the temperature difference? So during the expansion process of a turbine, you might have some heat loss or gain, meaning you might have some heat transfer, but we don't know what they are. So, but ideally speaking, we don't want these two, right? If it is an ideal process, we don't want these two, which means that we are then left with work out equals to delta H. Make sense so far? So this is the ideal case that we want. So this ideal case will mean that during this process, we are getting an isentropic process, an isentropic expansion process. So isentropic efficiency, as the name says, it is an efficiency for the isentropic process, which means that we are actually measuring how close this turbine is to the ideal case. Meaning so by introducing this isentropic efficiency, you no longer need to, meaning we don't need to care about the Q out, Q in anymore. So if we know that how efficient, like what is the isentropic efficiency of this turbine, if you apply this efficiency into the turbine, then it means that we account for that heat loss or heat gain of the turbine itself. You get what I mean? So essentially it's just how close the turbine is to be the ideal case, which is the adiabatic case. Okay, so the isentropic process involves no irreversibilities and serves as the ideal process for adiabatic devices. So which means with this you don't need to care. Either way, you can still use back this equation. We don't need to care about the Q in and Q out anymore, because if the moment you multiply in the efficiency term, then you will get the actual work. So you can see from this equation, basically. At the bottom, you get an isentropic turbine work. At the top, you get an actual turbine work. So if we are talking about a turbine here, a turbine extract work, the actual work will always be that you can extract will always be lower than the ideal work that you can extract, right? Because the actual one will involve some heat loss. So if some of the energy is lost to heat, then the work out that you get will be less in that sense. So the actual work that you get will always be less than the isentropic process. So you can also see from this HS diagram here, you can see that if it is an isentropic process, it will just go all the way straight. But if it is an actual process, then it will go to the right. How do you know which direction it goes? It always goes to the right, because entropy always increases. So it always goes to the right. So then you get this equation here. So this equation is used to calculate the isentropy efficiency. So H2A is the actual 2A. Basically, the actual H when it is at the actual H at state 2. H2S is the isentropic enthalpy at state 2. Then for ideal gas, so this one involves a bit of derivation. Basically, it is just this one. Then we cancel these two off, so it's just a change difference in the temperature. Okay, so this is the case for a turbine. Then let's say we look at compressor and and pump. So compressor, so again, turbine is the expansion process. Compressor and pump is a compression process. Okay, so similarly, the main point for a turbo compressor will be work in. So it's essentially just H2 minus H1. Right? So let's say if we go back, we use back the general equation, you cancel off. Ideal case for a compressor and pump, work in would be the change in enthalpy as well, m dot H2 minus H1. So for the isentropic compressor work, then in this case, you will notice one very weird thing. It looks similar, but we swap the denominator and the, what do you call the other one? Forgot the name, but anyway, we swap them. Why is that the case? Because you can see, we are keeping the same pressure. That's why if you are keeping the same pressure, turbine, the actual work that you extract is less than the ideal work that you can extract. Makes sense, right? So for pump and compressor, we are also keeping the same pressure level. So meaning now, we want your compressor to do the same thing. If you want to compress 100 kilopascal to 1 megapascal, whether it's actual or isentropic, we are still doing the same pressure change. So obviously, the actual one, you will need more effort to do the same thing, because due to irreversibilities. The ideal one, you need this much work. The actual would be more work, which is why then in this case, since we are still dealing with efficiency, right, we always want this value to be less than 1. So for the compressor work, then the actual work is actually at the bottom, while the isentropic work is at the top. So these two, you need to be a bit careful. So you again go by the same logic that I mentioned just now. You can actually then remember which one is at the top, which one is at the bottom. The larger value should always be at the bottom. Okay, so other than that, it's the same thing. You replace it with H2 S and H2A. For ideal gas, you replace with T2S and T2A. So for pump, then you can also replace the H2S minus H1 with Vp2 minus P1 as we derived earlier in 2 slides before this. So in the HS diagram, you also can see the same thing. The actual process goes to the right, the value of H2A. Alright, so these are the 2 main things actually, meaning for compressor and the turbine, because in your future chapter you will also come across these 2. Okay, maybe more for this semester you come across compressor, probably not turbine. But yeah, same thing, you still need to know this one. So next we have one more thing here, which is nozzle. Okay, turbine also will involve this, but so again, like I said, isentropic efficiency, we can apply this to everything that where their primary job is not heat transfer. So if you are talking about evaporator, condenser, then this cannot work. But nozzle, its primary job is to change the velocity. Right? Its primary job is to change the velocity of the fluid. So now for the derivation, I won't go through this. It basically just that you cancel everything off, then you will left with the kinetic energy term. So for nozzle, then the efficiency we approximate it to V squared 2A, so the actual one, over the isentropic one, which we also can say that we also can put it in terms of enthalpy. So these 2 equations are equally available. Again, it's similar equation to the previous equation. So this one H1 minus H2A, H1 minus H2S. Again, the higher value minus the smaller value. So when it goes through the nozzle, ideally speaking, there's no heat transfer, velocity will change this way. But if during the nozzle part you have some heat change, there are some loss in energy, then the velocity that comes up will be less. So the actual one on top. Alright, so this way then now we try to look at this. So steam enters an adiabatic turbine at 7 megapascal, 600 degrees Celsius and 18 meter per second. And it leaves at 5 kilopascal, 50 kilopascal, 150 degrees Celsius and 140 meter per second. If the power output of the turbine is 6 megawatts, determine the mass flow rate of the steam flowing through the turbine and the isentropic efficiency of the turbine. Okay, so this one actually the diagram not very important, but let's say what we have here. Okay, so at the inlet you have P1 equals to 7 megapascal. T1 equals to 600 degrees Celsius, and again, if the question gives you the velocity, just make use of it. So V1 is 80 meter per second. So P2 is 50 kilopascal, T2 is 150 degrees Celsius, and V2 is 140 meter per second. Okay, so this question in a way is actually very easy. Why? Because you are actually given almost all the information. Okay, so just by looking at this, I don't really need you to solve. I will solve it with you, but tell me, how can you obtain the mass flow rate of the steam? So the assumption here, again, the standard assumption, steady flow process, potential energy change is negligible, kinetic energy is not negligible since you are given the value. The device is adiabatic. This one, technically speaking, okay, you need to put it in because otherwise you cannot. No, actually you shouldn't put device is adiabatic. So actually this one shouldn't be there because you are not in a way you are not talking about the, because you need to find isentropic efficiency. If there is an isentropic efficiency, then it is not negligible. But for now, maybe just leave it here first. Okay, so now how do you find this? Now for this question, again like I said, one thing is very straightforward, because the inlet and the outlet are both given to you. Almost all the information. Okay, so there's only one inlet and one exit, so we know that mass flow rate is a constant throughout this whole thing. So we know that E in equals to E out, so we derive this equation, we come back to this. Okay, so I actually wrote that back, so then don't need my messy writing. Okay, so for this question, yeah, so the initial way, to be fair, I think this example, this method of solving is not 100% correct, because you still need to find the isentropic efficiency, but we keep it to that first. So initially, we still assume that it is adiabatic, otherwise you cannot actually solve this question, right? So we go with this general equation first. We assume it is adiabatic first, or else you cannot solve the equation. So you can solve. Okay, never mind. I think that explanation is not very good here either. Okay, let's put it this way. I think let me change a bit the way that I explain. Because just now I mentioned this, right? When we use the isentropic efficiency, we take into account all this heat change. That meaning we don't need to know the actual value in order for us to. We don't need the actual value of the Q in and Q out in order for us to find out what is the difference between the work without, the actual work and the isentropic work. So which is why when we solve this kind of question, by using the isentropic efficiency, we can actually just assume that the heat is negligible first, so that because they are taken into consideration already. So here, so from something like this. So here, we cancel off the Q. You move things around, then you are left with this equation. So work out is given to you. Right, so work out is given to you, then you can find out H2 and H1 from the table. And then the velocity is also given to you. So now one thing that you need to be clear about here is this. Is this H2A, so whether this H2 here is H2A or H2S. All the information that are given to you in the question. So if if you look for the thing based on what is given in the question itself, it is always the actual value, not the ideal or isentropic value. Okay, so every information that's given by the question. So if you look for this, so now this H2, we are looking for it based on 50 kilopascal and 150 degrees Celsius. So this is the actual condition of the outlet of the turbine. So what you are finding here is H2A. That's why I say we can just ignore Q in and Q out, because this H is already based on all the after all the losses. Okay, so this is the actual H. So then we go through the usual process. Now, P1 and T1, we say that this is we know that it's 7 megapascal and 600 degrees Celsius. So H1 is 3650.6 if you look at the table. The question also look for S1 here. For now, you ignore first because you don't know what is that for. Second state, H2A. You can get H2A from 50 kilopascal, 150 degrees Celsius. So by substituting all of this into the equation, then again velocity, don't forget to divide by 1000. You will get the mass flow rate. Okay, so the first part, very straightforward. what you have learned before this. Alright, so here we just ignore everything, you know that this is what you have learned. Okay, then you need to calculate the isentropic efficiency. So what we mentioned that just now, this H2 that you found is H2A, right? Which means we need H2S in order for you to find the isentropic efficiency, because that's the equation. So now the question here is how to find H2S. So to find H2S, you need the state that H2 as state. You need state 2S. Then only you can get H2S. Right, the isentropic case. Yeah, so we know that state 2S is actually when it is an isentropic process, meaning entropy doesn't change. This is also why at first we found this. So once you know S1, okay, this one is the equation. So based on this equation, we know that we need to find out what is H2S, or you can also find work out as actually it's the same thing. This is basically just work out the actual one over work out the isentropic one. Okay, so this is actually the equation that we talked about. So it doesn't matter. So what we want now is H2S. Right, and so based on H2S will be when S2 equals to S1. So before I go to the next slide, okay, while you are also taking photo or copying, now, so we know that for state 2S, let me write here lah. But this is in the next slide as well. You don't really need to copy this. We know that S2S is equals to S1, but we need one more information, right? In order for us to find H2S, what is that one more information? No. There's no quantity in this case. Because there's no information on that as well, so we cannot assume that. The hint here is in the diagram. It is also something that I actually forgot to talk about just now when I talk about isentropic efficiency. So try to observe. Pressure is another thing that you can take. So P2 is still 50 kilopascal. So we can, of course, you are not going to assume P2 equals to 50 kilopascal, T2 equals to 150 degrees Celsius, because if you assume both of them, then you're getting back H2A again. So one of them will actually remain constant. So let's go back to this. Okay, so you will notice that in all of these diagrams, we assume that pressure is a constant. So obviously, we know that actually in actual cases, when it pass through turbine, it will pass through pump, it pass through nozzle, there might be some pressure drop. Again, due to irreversibilities. But of course, we cannot assume everything also drop or change. Then you cannot really solve. So in our case, always remember this. Pressure is something that never changes during isentropic process. So if we say that this thing is going to work between these two pressure, it is going to work between these two pressure. It doesn't change. So in this case, so you can see all of this, we are both working at the exact same pressure, P1, P2. So like this, so the isentropic version work until this pressure. The actual one also goes to this pressure. It's always the same thing. The pressure never change. Okay, temperature might change, but pressure does never change. So same thing here. In this case, P2 is 50 kilopascal, which means now at the outlet, let's see first. Now we are just check this one. Let's go through. Okay, so again back to what you know about the table. We know that S2S is equals to S1, And just now I mentioned P2 is still 50 kilopascal because it is going to be a constant. So you check with SF at 50 kilopascal, you check with SG at 50 kilopascal. Now you can see that S2S is between these two value, SF and SG, right? Then now you know, then only now you know that you should find the quality. So even though just now I say quality is wrong, that was because you don't have enough information to know whether you need to find quality or not at that point. But now that you know that based on 50 kilopascal, SF and SG, the S1 value is between S2S value is between SF and SG. Then now you need to find the quality. Wait, why is this value so big? Oh, SFG, sorry. So here, based on this equation, you need to find X2S, then you sub into this value to find H2S. Okay, so after that, yeah, I mean it's there after already. Okay, so based on that, based on the S2S value, you can find X2S, and then based on the X2S, you can find H2S. So now you have the H2S value. Then you need to find then you can find the workout. Then after that, you can sub this into the isentropic efficiency equation. So in this case, the isentropic efficiency equation, right, will be more accurate if you use this version instead of this version. Because here, when we derive this version, the bottom one, it's assuming that there is no change in KE and PE. So now, the term, that's why that is the equation. It's basically the workout over workout. Then we cancel the M. So in this case, since you have velocity, the more accurate version will actually be the work over work instead of delta H over delta H lah. But again, actually, if you forgot the velocity, it won't actually affect the. Let me see, will it affect much? Yeah. If you forgot about the kinetic energy term, right, it actually won't affect your outcome too much, because again, like I mentioned, kinetic energy term usually don't really have much effect on the change in the energy itself, because the value is actually very small. As you can see here, 140 square minus 80 square, then you divide by 1000. Once you divide by 1000, the value will drop a lot. Which is again the main reason why we always ignore KE, even if there is some changes there. Can I understand? Okay, so the next slide basically is just to finish up the question. You can see that this is the 73.4%. So again, I believe that if you decide to use H1 minus H2A or H1 minus H2S, you should get about the same value as well. It shouldn't affect the value too much. okay, we have a bit more here. Let's just quickly wrap this up. It basically just talking about entropy balance. So entropy balance is basically the same thing as the energy balance. Okay, so the whatever that you calculated is about the same. So total entropy entering a system minus the total entropy leaving the system plus total entropy generated. So remember, we always have generated entropy. So this one we always have one extra term. So entropy, unlike energy, in a way it can be created. That's why it's not reversible, because you cannot come back. So it will be equals to the change in the total entropy of the system. If you have a reversible one, then the generator is 0. So the okay. So for closed system, the entropy change of a closed system during a process is equal to the sum of the entropy transferred through the system boundary by heat transfer and the entropy generated within the system boundaries. Yeah, actually that's about all. There's nothing too much I want to say here. For the closed system, the entropy change is mainly due to heat transfer. There is no entropy change due to work for a closed system. So unlike the open system part, we will have that, but for closed system, no. Alright, then for an isolated system, then obviously you don't get anything. So actually the entropy balance here is more like a summary of everything. Here, I think this one I will leave it for you to read. It doesn't really affect much of what we studied before this. Yeah, actually this one not too important. So I will end here. And next week we will enter a new chapter actually. So by this way, right, actually we should be able, so next week is week 10. We most probably can finish in week 11 actually. The next following 2 chapters usually I need 1 week or maximum 1 week and a half, 1.5 week. So then after that, okay, so here is the current plan. Remind me to mention this again on next Tuesday if I forgot, or the next Tuesday. So the current plan is we'll finish this up most probably before week 12. We will finish this. Then after that, we will discuss some past year 1 or 2 recent one. Then we have 1 2-hour class in week 12 where we will clash with the Malaysia Day replacement class. Replacement holiday. So because we are on time, I think we don't replace that one. It's fine. But on paper I still need to replace. So I will just put it on that Saturday. You guys don't need to come lah. But then like I said, Tuesday remind me again because not everyone is here. Alright? So basically for now this is the plan lah. We can finish before week 12, then after that we will discuss past year, then that's about all. Alright?